This presentation is about the Trapezium Rule. Lesson objectives. To be able to use the Trapezium Rule to approximate the area under a curve. Consider the graph below. It is the graph of y equals sine of x squared plus 3. If we want to find the area under the curve between x equals 1 and x equals 3, we would not be able to use definite integration, because we don't know how to integrate sine x squared plus 3. So what we do is we split the area up into a series of trapeziums with equal width h. For example, if we split the area into 4 trapeziums, we would have h is equal to 0.5. So there's one trapezium, second trapezium, third trapezium, fourth trapezium. And then by summing the areas of these trapeziums, we approximate the area under the curve. Now, if you do this for the general case, it leads to a general formula called the Trapezium Rule, which is in the formula booklet. So we make our trapeziums, and dot dot dot, we're going to do a general case for any number of trapeziums, or a couple of trapeziums at the end. Now, to explain this formula underneath, we need to be able to use the correct notation. So y0 is the length of the first line, y1 the length of the second line, y2 the length of the third line, and this would continue up to the end. The last line will be y to the n, penultimate yn minus 1, the one before that yn minus 2. And then the trapezium rule, with h being the width of the trapeziums, is the integral between a and b of y dx is approximately equal to half h, open bracket, open another bracket, y0 plus yn, close bracket, plus 2 times, open bracket, y1 plus y2, all the way up to yn minus 1, close bracket, close another bracket. And we're also told that h is equal to b minus a divided by m. So in this example, we're to use the Trapezium rule, first of all with 4 strips and then with 8 strips, to estimate the area under the curve with equation y equals the square root of 2x plus 3 between the lines x equals 0 and x equals 2. So starting with 4 strips, we have a table. This is a common for a table to be there for a C2 exam. Now we'll need to work out the y coordinate, so when x equals 0, stick 0 into the square root of 2x plus 3, we get root 3, stick x equals 0.5 in, we get 2, stick x equals 1 in, we get root 5, stick x equals 1.5 in, we get root 6, and stick x equals 2 in, and we get root 7. Now it's best to denote what the y coordinates are, so y0 is root 3, y1 is 2, y2 is root 5, y3 is root 6, and y4 is root 7. So n is 4 for this. Now the h, we don't actually have to use the b minus a over n if we're given the x coordinates in a table, because the h is the distance between any pair of x values. So in this case, h is 0.5. And you could use any pair of x values to show that h is 0.5. The area, therefore, will be a half of h times y0 plus y4, the first plus the last, plus 2 times all the middle terms added together, y1 plus y2 plus y3. So sticking our values in, we've got half times a half times root 3 plus root 7, first plus last, plus 2 times all the middle terms, 2 plus root 5 plus root 6. Sticking all of this into the calculator correctly, we get 4.4372 to 4 decimal places. Part B, same idea but a bigger table for more strips. So we stick our x values in, so x equals 0 gives y equals root 3 again, x equals 0.25 is root 3.5, x equals 0.5 is 2, x equals 0.75 is root 4.5, x equals 1 is root 5, x equals 1.25 is the square root of 5.5, x equals 1.5 is root 6, x equals 1.75 is the square root of 6.5, and x equals 2 equals the square root of 7. Now, labelling them again, y0 is root 3, y1 is root 3.5, y2 is 2, y3 is root 4.5, y4 is root 5, y5 is root 5.5, y6 is root 6, y7 is root 6.5, and y8 is root 7. Distance between the x-coordinates is the h, so the h is 0.25. So the formula we need in this case is a half of h times first plus last, y0 plus y8, plus 2 times all the rest added together, y1 plus y2 plus y3 plus y4 plus y5 plus y6 plus y7. Sticking in our values, we get a half times 0.25 times root 3 plus root 7 plus 2 times root 3.5 plus 2 plus root 4.5 plus root 5 plus root 5.5 plus root 6 plus root 6.5. Calculating correctly to 4 decimal places, this gives 4.4403. Now in this case, it is actually possible to do the integral exactly. So the actual area is 4.4414 to 4 decimal places. So the h strips is closer than the 4 strips. And in general, this is usually the case, that the more strips you use, the better the approximation, as the trapeziums more closely match the actual shape of the curve. This concludes our presentation.